So let me finish off what we were studying and then start on a new topic today. So, so far we have considered systems in which we vary the energy, right? So, so far we have only considered systems, where the only variable, the only only macroscopic, independent variable was the energy, right? So, but when we did thermodynamics, we saw that for fluids, we have more things to play with. For example, for fluids, volume also becomes an independent variable, right? So for solids, not so much, but for fluids, we can vary the volume by increasing the pressure and stuff like that. So in principle, our entropy should be a function of both the energy and the volume. And the number of possible configurations should take into account not just the energy, but also the volume of the system. And this is something that we will see in example when we do, for example, classical gases. So we will see examples of this in the future. But now let's define, now that we can vary volume, let's define a new quantity. And this new quantity, let's call this pressure. Okay? So pressure, small p, somehow pressure is, people use a small p for pressure, I don't know why, is temperature times ds by dv. And now the partial derivative is important because it implies that we are keeping the E variable constant. So, if I wanted, I could have written like this, right? But I don't have to. Whenever you have partial derivative, it's implied that all the other dependents are kept constant. Okay. Now, something that we have done before is that we have shown that, when we bring two systems together where the total energy is constant, then we find that the principle, we are naturally led to the system where the state of the system where the entropy is maximized, and therefore, we have thermal equilibrium. Now, suppose similarly, we do the same thing, but now, in addition to thermal contact between the system, so we have a thermal contact, we also have the two systems are separated by a movable wall, okay? So we can imagine, say, we have an adiabatic container, not adiabatic, you mean thermally insulated container, and inside, we have a dithermal wall. So this wall is dithermal, meaning that heat can, go through. And over here, we have a gas which has volume 1, and over here, we have a gas which has volume 2. And this wall can move about, okay? So we start with some initial condition, and then we let it go and let it come to equilibrium. So as before, if I do the same calculation again, which I'm not going to do, but I'm going to leave it as an exercise for you to do, we shall find that we get thermal equilibrium condition as before. Where T1 will be equal to T2, but there will also be mechanical equilibrium. Okay, mechanical equilibrium, which will be P1 is equal to P2. Okay, the two gases will come to the same pressure. So now we're in a position to derive from statistical mechanical consideration the first law of thermodynamics. So far, we have derived the 0th law and the second law, right? But we have not derived the first law yet. So the definition of pressure we had is this. And apparently, it looks like pressure depends on entropy. But that's actually not the case. And that's because, recall the definition of temperature. The definition of temperature tells us that the first term, first factor can be replaced by this. And therefore, the entropy dependence cancels out from the definition of pressure. Okay? So, so I see that Nahi has come. Anyone else who is here who I didn't, who came late and I didn't give you attendance? Okay, so let me carry on.
Sir, I have a question.
Yes.
Omega of E, we used omega of E, but what's the change so that we are considering omega E and V? The volume and energy varied before as well, right?
Not in the statistical mechanical part of the course. In the thermodynamics part of the course, yes, we varied energy and volume. But when we started statistical mechanics, we were just considering the energy of the system. We did not consider so far volume dependence. So what I'm saying is that if you consider volume to be an independent variable and you allow entropy to depend on volume, then the maximization of entropy that we saw leads us to the conclusion that two gases which are in thermal contact with each other and are separated by a movable wall, that equilibrium will be reached when the temperature is equal as well as when the pressure is equal, or pressures are equal, okay? And we'll see some examples later, okay? So this is left as an exercise, to show that this is true, okay? That this is true, okay? This is left as an exercise. And it's very easy. It's just repeating what we did for the temperature, okay?
Sir, was my attendance taken?
I don't think so. You came probably a bit late, right?
3 minutes, yes.
Yeah, okay, yeah. All right, so Medad is present as well, okay. All right, so let's move on. So this is the definition of the definition of pressure tells us that it's given by dE by dV. So this means that if I now change the entropy, well, the entropy is now a function of energy and it's a function of volume. And we have seen that we can write the pressure so this is the definition of pressure. So if I use the definition of pressure and the definition of temperature, then we can rewrite this expression as dE is equal to d of Ts minus P of dV. And this we recognize as the first law of thermodynamics. So all of these things follow very easily from the fundamental definitions. Okay, so in the first law, we have two terms. The P dV term is the work done by the fluid. And the way to understand this is that suppose we have a fluid in a box and it had some piston on it. Then suppose the cross section of the box is A, and then the force that the fluid is putting on the piston is F, and suppose that it moves the piston a distance of dx, then the work done by the fluid, is going to be F times dx. But of course, F divided by A times dx is pressure times dV. And therefore, we think of P of dV, the work done by the fluid. And the thing is that when the fluid does work, it loses energy. It gives up some of its energy, and that's why we have this minus sign over here. So what is the meaning of this term? Obviously, from dimensional grounds, it must also represent some sort of energy transfer. And this energy transfer is what we have called heat in our analysis of thermodynamics. So just to summarize, P of dV is going to be the work done by the fluid or the gas, and T of ds is the energy transferred I think double R, transferred due to, or energy transferred by heat, okay? Again, let me remind you, heat is not energy, it's a way of transferring energy, right? And then we can then define heat capacities. So we define heat capacities, and it's a very important quantity, and that's because it tells you how much energy can be transferred to the system, due to a change in the temperature, okay? And so there can be heat capacities where we keep the volume constant, and there can be heat capacity where we have the pressure constant as well. Okay, so we'll see some examples of this later on. So this is basically all I have to say about the microcanonical ensemble. And now I want to move on to the next topic, which would be the canonical ensemble. But before I do so, any questions?
Sir, I kind of noticed that there was no link to the back channel given today.
Oh, there is if you go look at the general. Oh, sorry. And I gave it to the wrong place. Yeah, sorry. Yeah. Okay. Yeah, I just gave it to the general discussion. Yeah. Okay. Sorry. I gave it to a
Happens to the best
private.
of us.
Yeah. Thank you. Yeah. All right. So please give me your questions in the back channel chat. Okay. So that'll be appreciated. All right. So, any more questions?